Hello everybody. This video will be showcasing the hardware experiments for testing optimal navigation algorithms which were conducted in the Control and Instrumentation Laboratory of Indian Institute of Technology Guwahati during 2014 and 2021. The experiments have been designed and conducted by myself when I was a research scholar with IIT Guwahati under the supervision of Dr. Indrani Kar. This video will be briefly talking about the control architecture, hardware assembly, software applications, communication, system integration, data acquisition, storage and analysis pertaining to the navigation of mobile robots. The hardware comprises of an onboard computer which is piggybacked on a mobile vehicle. The mobile vehicle acts as the pursuer. The onboard computer is termed as a server. Two other small-sized autonomous vehicles act as mobile target and obstacles. The target and the obstacles have been designed to execute a predetermined set of trajectories which are unknown to the pursuer. An off-board computer is used to compute optimal trajectories for the pursuer by taking into account the current states of the target and the obstacle. The off-board computer is termed as the client. A ceiling-mounted camera is coupled to the client and configured to read states of the pursuer, target, and the obstacle. The pursuer has encoders and inertial measurement units attached, which gather state information pertaining to the pursuer. Trajectory generation and execution are performed with shrinking horizon model predictive control policy. The pursuer is implemented on PetrolBot, a research-based autonomous mobile robot by Adept Mobile Robots. It is a two-wheel differential drive system with a saturation velocity of 1.8 meter per second and a saturation turn rate of 300 degrees per second. The PetrolBot is configured to carry a piggybacked server that communicates serially with the internal firmware of the robot. The robot is configured to accommodate image-based markers, onboard cameras, ultrasonic sensors, inertial measurement units for supporting various navigation-related experiments. The target and the obstacle are configured as small autonomous robots which can execute a commanded trajectory. Sensors associated with the experiments include a commercial-grade fixed-focus webcam of 720p resolution that can collect images at 30 frames per second. A 6-axis inertial measurement unit MPU 6050 has been attached to the chassis along center of gravity of the vehicle and has been controlled by an Arduino Uno programmable microcontroller connected to the server. The PetrolBot has a pair of quadrature encoders associated with the driven wheels for odometric measurements. The target and the obstacle robots are associated with image-based markers, each being unique and asymmetric for identification and localization. The IMU offsets are calibrated in static conditions and tested by applying uniform motion along the axis using I2C and MPU 6050 public libraries associated with Arduino controller. The measurements obtained from the accelerometer and gyroscope are serially transmitted from the Arduino controller to the server computer encoded in a 50-bit data format. The server further transmits the information to the client for computation of optimal trajectories. Unity3D graphical user interface is used to visualize movement of the target, obstacle, and the pursuer. Image-based markers attached to the top of the mobile vehicles are unique asymmetric images that are detected by the overhead camera and identifiable by AR Toolkit. Augmented reality allows virtual placement of a colored box on an identified marker. Position and Euler angles of the marker are obtained with respect to the camera frame and serially transmitted to the client in 16-bit long data packets. Homogeneous transformation is used to convert the localization information obtained with respect to the overhead camera to any arbitrary point P on the motion plane. The local frame of reference is a projection on the motion plane and is customizable by appropriate calibration of the offsets observed in the camera readings. The offsets are verified by the measurements against ground truth. Once the local reference frame is fixed, all other points on the motion plane can be referred to as translations along x, y, and z axes with respect to the local reference frame. Transmission of Euler angles and position of a marker object from the overhead camera to the client is carried out serially using user datagram protocol. Changes in the states of the marker object can be visualized in real time by clicking on the marker object option under the project name on the Unity3D GUI. The offsets of the states may be adjusted and plotted from the client-side program. In each iteration, update of state information of the target and the obstacle is available from the camera. Using this update, optimal controls and optimal guidance trajectory for the pursuer are computed. Boundary values for the optimal control problem are estimated using polynomial extrapolation at the client-side computer. Using actual state feedback of the pursuer from the wheel encoders and the IMU, and that of the target and the obstacles from the overhead camera, optimal trajectories are computed iteratively in real time using shrinking horizon model predictive control policy. Thereby, the optimal trajectories shift slightly with increase in the number of iterations. The optimal guidance trajectories act as reference trajectories for path and control variables. The reference values are transmitted by the client computer to the server computer. The server transmits the commanded trajectories to the firmware of the petrol bot, and execution is performed by built-in PID controller. The feedback-based tracking control is also operated by the client. The client-side code has been written in MATLAB. The video shows setting up of connection between the server and the client through ad hoc network supporting serial transmission. The commanded trajectory can be a time sequence of path points or a set of control variables. Augmented reality component in the Unity3D graphical user interface is the red block placed on the detected marker object. The camera data connected to the client and the encoder measurements connected to the server are obtained by serial communication and plotted for visual verification. Data from the inertial measurement unit encoder collected by the server are configured to be stored in shown format in text file for future reference. The server-side code has been written in C++ in association with the ARIA library for PetrolBot. The transmission and reception processes have been performed in sequence by socket programming. Pose, acceleration, and angular velocity of the pursuer are transmitted at a predetermined periodicity depending on the processing speed of the camera. The data packets are transmitted using user datagram protocol, which supports real-time data transfer. A predefined time interval referred to as the idle time has been used to check transmission status. Inactivity beyond the idle time triggers resetting the communication link and preventing stalled motion condition. Thus, a customized handshaking routine has been developed to supplement the absence of numbered data packet transmission. The server is provisioned to display the real-time collection of sensor data after the client-server connection is established and the PetrolBot is activated. The execution file initializes the real-time display portal. The real-time data is written in a file until the connection is terminated, that is, communication reset does not affect data acquisition and storage. The file can be accessed by the client for data analysis and calculation of real-time optimal trajectory in each planning iteration.